Hey everybody. We're going to be going into another area of kinetics. We have to look at how to measure the rate of a reaction. How do we measure how fast the reactants become products? Rate of the reaction is how fast the molecules go from reactants to products. And we're going to take a look at Alka-Seltzer tablets first. If I were to drop an Alka-Seltzer tablet into water and I asked you to, hey, figure out a way to measure the rate of the reaction. Some of you might say, hey, you know what? Let's take a look at the tablet and see how fast it takes for it to disappear. In which case, you would be looking at the change in the concentration of the reactant over time. Some of you might say, you know what? I think it would be much neater to look at the production of the CO2. So you would look at the change in the concentration of the product over time. Either one should give you the same exact value. That's a P, sorry. They should give you the same exact value because we are talking about the same reaction. The only thing that we have to consider is that a reactant's being used up and a product is being produced. I'll show you what I mean here. If we were to look at how quick a reactant is being used up, and I did change. Now remember, change is always final minus initial. So if I do final minus initial here, and I take a look at this data, so time 0 and at time 35 seconds, I had 5 grams and I had no grams of tablet. So if I were to take a look here, I would say 0 minus 5 over 35 gave me my rate of reaction. For this over here, looking at the production of the products over time, it would be 5 minus 0 over 35. They're almost the same. They're the same in magnitude, but opposite in sign. To make them truly equal to one another, wherever we're looking at reactants, because their concentration goes down, we have to negate it. So this negative sign becomes very important for any time we're using a reactant to determine the rate of reaction. If we have to put a negative change in the concentration of the reactant over the change in time. Here I'm just showing you again the concentration of A decreases over time, B increases over time. To set these equal to one another, you have to negate it in order to make them truly equal to one another. What happens though if we go to measure this reaction and I send somebody into the back to measure the disappearance of A and somebody measures the disappearance of B? What happens is the person that's measuring A is going to say, wow, it's disappearing so fast. B is disappearing slower, and that's because of the coefficients in the chemical reaction. It's a 2-to-1 ratio. So A is going to disappear twice as fast as B, but yet it's the same reaction. So what we have to do is make sure that these are truly showing the same story. We do that by, in the rate law, setting them all the coefficients equal to 1. So we want to set coefficients equal to 1. So how do you do that? Have the rate law for that example here. If I'm looking at A is a reactant, which is why the negative sign is there. I'm putting 1/2 here because I do want to set all the coefficients equal to 1. So if this is a 2, I would have to multiply it by 1/2 in order to get to 1. Change in concentration of A over change in time, that's the same. Then, if I take a look at B, again, negative sign because it is a reactant, but this time my coefficient is 1. So I don't have to multiply it by anything, change in concentration of B over change in time. The product, I don't need the negative sign, but I do have a coefficient of 2, so I multiply it by 1/2. Now, all the rates should tell the same story. No matter who measures them, they'll come up with the same rate of reaction. And you could plug in your numbers here and actually try it. If you were to take, for example, A, it's 0.6 minus 1 over change in time, which is 25 seconds. It's a reactant, so I'm going to multiply it by negative sign to negate it. And then the 2 becomes 1/2. That should be equal to, again, a reactant, but this time we want to look at B. B is 0.8 minus 1 over 25, and then that should equal 0.4 minus 0 over 25. Remember, there's a 2 here, so we want to multiply this by 1/2. And all of these will now give the same rate of reaction. So it's just setting them equivalent to one another. Here's something kind of interesting. If you take a look at the rate of this reaction at these 3 times that I have here, the rate of the reaction actually changes and it gets slower as time goes on. So if it gets slower as time goes on, the question is, why does it get slower as time goes on? And it gets slower because of collision theory. So if I looked at the collision theory and tried to give a reason as to why this is slowing down, as time goes on, these reactants get used up. If there's a lower concentration as time goes on, then the reaction rate at the very end will be much slower than the reaction rate in the beginning. That's it for tonight. I'll see you tomorrow and we'll do some more work on this. Take care. Have a good night.